Okay, so after talking about different forms of energy, let us go to a new section talking about energy transfer. Okay, well, for energy transfer, it's not like the previous section, because in the previous section we are talking about some energy that stored inside system. But for energy transfer, it is not stored inside system, and we will discuss it in a further detail in this section. Okay, well, as most of the engineering devices, only the mechanical forms of energy are involved in the analysis. Okay, so it's beneficial to study more about what mechanical energy is. Okay, before we really talk about energy transfer, let us talk about more kinds of energy. Okay, so here we will talk about mechanical energy. Mechanical energy is defined as a form of energy that can be converted into mechanical work completely and directly by an ideal mechanical device, for example, like an ideal turbine. Okay, of course, it should be ideal. Otherwise, there should be some energy losses during the process. Okay, so we would say that there should be no any friction or other kinds of losses. So this kind of energy, if it can be completely converted into mechanical work, then it will be a mechanical energy. Okay, but for this kind of definition, it may be a little bit abstract for you. So what are the examples? Well, some of the examples are what we have seen before in our previous sections. That would be the kinetic energy as well as the potential energy. Okay. Strictly speaking, it should be called flow work because it is a form of work done by pressure. Well, although different people have different rationales in using flow work or flow energy, both of them reaches the same form of energy balance for flowing fluid. Okay. For flowing fluid, the energy balance is a bit complicated, so we will leave that in chapter 5. Well, in this series of handouts, we will follow the textbook and regard it as a flow energy. Okay, the flow work will be the flow energy because we can see in chapter 5 that it can greatly simplify the analysis. Okay, now we will derive the work done by the pressure. That is what we call the flow work. Okay, as you can see in this diagram. Okay, suppose I have a fluid element here, and we can see that there should be some pressure force that tends to push this fluid element out of this control volume. And we would like to find out the work done that we need to input to this fluid element so that it can get into this control volume like this. Okay, we would just consider the moment where this fluid element for the right hand surface, it touches this boundary. Okay, the dotted line is the boundary. Okay, when this surface of this fluid element touches this boundary, to the moment this left hand surface touches this control volume. That is, it just passes through this boundary to get into this control volume. Okay, here we will find out the minimum force or the minimum work done that we require, because here we will assume one thing. We will assume that there should be no or negligible acceleration in this case. Okay, we will assume negligible acceleration in this case, so that if you do a simple force balance in the horizontal direction, you will see that this force that we need to exert on this fluid element will be equal to this pressure force. Okay, so that the work done will be equal to F times S. That's the definition. And this F, by using force balance, we will get a P times A. And this S, because we are talking about just pushing this fluid element from here to here, and this gap is just exaggerated for easier visualization. Okay, so this S is actually equal to L because this surface, originally this surface touches this boundary, but after we have pushed this fluid element, it will having the left hand surface touching this boundary, so the displacement will be L. Okay, so that we can rearrange the terms by putting the bracket into A times L, and you will see that it will be equal to P times the volume, P times V. Okay, but in thermodynamics, we will likely to express this flow work by using a unit mass term. So we divide both sides by mass. Okay, divide both sides by mass so that we have a flow work per unit mass equal to P times small letter v. Okay, that's a specific volume. And recall that this specific volume is equal to the reciprocal of the density, so that we will have this one. That is P divided by rho. Okay.